Welcome to this video guide on limits and continuity. We will explore the foundational concepts of calculus, covering definitions, theorems, and techniques to help you master these essential mathematical topics. By the end of this video, you will be able to define limits, apply fundamental limit theorems, evaluate limits using algebraic techniques, work with trigonometric functions, understand limits at infinity, and identify continuous functions. What is a limit? Simply put, a limit describes the value a function approaches as the input gets closer to a specific point. It tells us where a function is headed, even if it never reaches that exact value. The formal definition of a limit is grounded in precision. We say the limit of f of x as x approaches a is L, if, for any small distance epsilon, there exists a distance delta, such that whenever x is within delta of a, f of x is within epsilon of L. Graphically, a limit is determined by the behavior of the function as we approach a point from both sides. For a limit to exist, the left-hand limit and the right-hand limit must equal the same value, L. Remember, a limit is about the journey, not the destination. The function's actual value at that point, f of a, does not necessarily need to equal the limit L, or even be defined at all. Let's look at an example. To find the limit of 3x plus 1 as x approaches 2, we can use direct substitution. Plugging 2 into the function gives us 3 times 2 plus 1, which equals 7. Theorems on limits simplify our work with complex functions. Rules for sums, differences, products, and quotients allow us to break down complicated expressions into simpler, easier to evaluate parts. Using these theorems, evaluating limits becomes straightforward. For a polynomial like 2x squared plus 5, we can use the direct substitution property to find that the limit as x approaches 3 is 23. When direct substitution doesn't work, we turn to other methods. Techniques like factorization, rationalization, and simplification are essential tools for handling indeterminate forms. Consider a case that results in an indeterminate 0 over 0 form. By factorizing the expression, we can cancel common terms, simplifying the function to a point where substitution becomes possible. Rationalization is another powerful technique. If an expression contains radicals, multiplying by the conjugate can help remove indeterminate forms, allowing us to evaluate the limit successfully. Trigonometric limits have their own special rules. Fundamental limits, like the sine of x over x approaching 1, are cornerstones of calculus, but always remember to keep your angles in radians. These standard trigonometric limits are derived from geometric properties on the unit circle. They form the basis for solving more complex problems involving trigonometric functions. Finally, we consider limits at infinity, which describe the long-term behavior of a function. Whether examining polynomials, rational, or exponential functions, we look at what happens as x grows very large. An infinite limit occurs when a function's value grows without bound, as x approaches a specific point. For example, in the function 1 over x minus 2, the values head toward positive or negative infinity. When a function approaches infinity at a specific x value, it creates a vertical asymptote. This vertical line represents a point where the function cannot be defined. Moving on to the existence of limits, a limit at a point x equals a exists if and only if both the left-hand and right-hand limits exist and are equal to the same value, L. If the left-hand limit and right-hand limit do not equal each other, then the limit at that point does not exist. It is essential to check both sides to confirm. Now let's discuss continuity. A function is continuous at a point x equals a if it is defined there, the limit exists at that point, and the limit equals the function's value. In simpler terms, a continuous function has no breaks, jumps, or holes. It flows smoothly through the point in question. When a function fails these criteria, we see different types of discontinuity. These include removable discontinuities, like holes, jump discontinuities, and infinite discontinuities. Understanding these concepts, limits, continuity, and their various forms, provides the essential toolkit for analyzing functions in calculus. Thank you for watching.